Today we're going to be doing Book 3, Proposition 32. And in this, we are trying to prove that angle FBD equals angle BAD and angle EBD equals angle DCB. And we're doing that from a given circle and a line and a point on that line that touches the circle. So, what we're going to do is we're going to use Book 1, Proposition 11, to raise a perpendicular, because that's what you can do with Proposition 11, from point B to create this line, BA. After we've done that, we have BA is perpendicular to lines EF. Now that we have that, we are going to create a random point called point C. And that's right here. So after that, we're going to use postulate 1 to connect all the lines. So we connect this line, this line, this line, and that line. So from that we get line AD, line DC, line DB, and line CV. And that concludes the construction. After we do that, we're going to prove that line AB is the diameter of the circle. And we can do that because of Book 1, Proposition, not Book 1, Book 3, Proposition 19. And we know that it's the diameter of the circle because we have these two are right angles because it's perpendicular and it goes all the way across the circle. So therefore, according to this proposition, it's the center of the circle. Now that we have this is the half of the circle, we know that this is a semicircle. And therefore, angle BDA is a right angle, because if you're given a right angle and the lines meet, then that angle has to be a right angle. And we know that because of Book 3. Know that because of Book 3, Proposition 31. And now we know, because of Book 1, Proposition 32, that angles DAB plus angles ABD are right angles. Because we know that this whole thing is going to add up to two right angles because of Proposition 32. And we know that this is a right angle, so therefore these two together have to add up to be right angles. And since we know that, we now are going to use step 1 and say that ABF is a right angle. And since we know that ABF is a right angle, that means that angle ABF is equal to these two angles added together. We know that because of common notion 1 that says if you have two things that are equal, the other two things will be equal. Now we're going to use common notion 2 and subtract angle ABD from both sides. So since we're subtracting angle ABD from both sides, we're then left with angles DAB equal to angle DDF, which is the first thing that we were trying to prove. So we can go ahead and start that. now that we've proven that, we are going to now use book 3, proposition 22, which states that if you have a quadrilateral inside the circle, the opposite angles are going to add up to 2 right angles. So because of that, we know that angle DAC, or DAB, plus angle DCB is equal to a right angle, and the angle ABC plus angle ADC is equal to a right angle. And now from that, we're going to use book 1, proposition 13, to say that angles EBD plus angles DBF are equal to 2 right angles. And we know that those are equal to 2 right angles because we know that they're equal to 2 right angles because they fall on this line. And whenever you have a line and you have a line coming off of that line, the remainders, or not the remainders, the angles of that line are going to add up to 2 right angles. So now that we have all of that, we can now say that angle DBE plus angle EBF is equal to angle DCB plus, now we have angle DCB plus angle DAB is equal to angle DBE plus angle DBF. And we know that because of common notion 1. And so again, we're going to use common notion 2, and we're going to subtract angles from those two sides of the equation. And the angle that we are going to subtract are actually these 2 angles because we already established that they were equal, so we're going to subtract them from both sides. And if we subtract them, that's going to leave us with angle EBD is equal to angle DCB. And we know that because of common notion 2, which says that if equals are subtracted from equals, then the remainders will be equal. And we can finish this proof with QE.